Oh, I already started it. Oh, what's up, guys? All right, cool. So let's get this set up. I'm just waiting for it to pop up here. And, ooh, am I having network issues? Let's make sure. Um, nah, we're good. All right. So let's have some fun. It's almost spring break. It is the last week before spring break, and that means it is almost time for your first exam. I am sure that everyone is full of nervous fear, and with good reason. I will destroy you. No, it'll be a fine exam. Don't be too nervous about it. It will be, I hope, at least sort of challenging. If you've been slacking off on the homeworks, I think you'll find it difficult. If you've been keeping up with it and feel like you're understanding the material, then I hope it won't be. Or I hope it'll be pleasantly challenging. Yeah. So a couple of homeworks this week, a Wednesday and Friday. They're shorter assignments. I've already got the keys up there ready to go. Those will automatically reveal when the due date hits, so you can check everything really quickly as we get ready for this exam here, which will release on Thursday. Fun. So one thing that might help you out a little bit as let me adjust my chair a little bit here. Let's see, is that better? Yeah, it's probably better. Okay, sorry, I was at a weird angle right there. I don't know if that's better. All right, bada boom. Okay, so one thing that will definitely help you out a little bit on this homework is a generalization of the deformation theorem that is pretty easy to prove and is a great little thing to discuss. It's an example, a worked example in your textbook, but it is worth bringing up quickly just in case you're one of those people who doesn't actually always read their textbook. It's also really easy and is a good place to lead into what we're going to talk about today with Cauchy's integral form or integral theorem, the integrals of Cauchy type and the integral representations of functions and their derivatives in the complex plane. So this is an example from section 2.2 actually, so a little bit ago. It says that if you've got a curve gamma that looks like here, let me just even highlight it out. There we go. It looks like this guy right here or something. You got some big curve, and then you've got a couple of different small curves inside of it, and you have a function that is analytic on the region between those curves. So that is on like all this space. Then you can analyze the contour integral around the whole thing just by summing up the contour integrals around the little pieces. And so the way to see this is just to do a fancy little trick like this. Here's the picture to think of. Basically, you're gonna go like into like the first one, and then you're gonna go around it, and then you go right back. And so you go in, go around it, go right back, go in, go around it, go right back, and so on and so on. And as you might notice, when you go down this way, you come back that way. And so you should be canceling everything out on these paths. Of course, the technical distinction right here to notice is that since these would not be nice paths, they would be overlapping themselves. What we really maybe should do is we should take like a tiny little distance right here between it, and then some like little distance epsilon, and then it's a weird epsilon, and then shrink that down to 0. But ultimately, this is perfectly fine to think of it this way. And the idea is that, like the down and back, the gamma and the negative gamma or so, cancel each other out. These little gamma tildes, as I believe they call them right here in the picture. So you have a gamma tilde and a negative gamma tilde to get back out of it. And there you go. That's the whole business of it. So if you want to evaluate, say, a contour integral, and there's two different points maybe where the function is not analytic, right? So you've got like 1 over z minus 1 and z plus 1. And you're going to do the integral around gamma, where gamma is, say, the circle of radius 2 centered at the origin, right? Then that would enclose both 1 and minus 1, which are no good right here, right? We're not analytic at those points, yeah? So you could split it into 1. You could go circle of radius 2, and you've got like 1 and minus 1, and you could just get 2 small non-overlapping circles. Instead of doing gamma, you could get like gamma 1 and gamma 2, and then you could evaluate this guy by just integrating over gamma 1 and then integrating over gamma 2 and adding them up. So you may find that a helpful trick on some of your homework. I'll leave it at that. If you find yourself struggling with a problem, I believe particularly in homework 7, you may find that a useful trick. So, on to, oh, am I frozen? Let me see. It looks like I'm frozen. Let me make sure we're not bugging out here real quick. Or at least Twitch is frozen. Nope, it's back. Okay. Hopefully there's no big problems there. Hopefully, yeah, it's kind of doing it again. Maybe I just have bad internet right now. Yeah, all the same. Maybe I'm just a few minutes behind on the stream. Okay, so we're talking about Cauchy's integral formula in section 2.4. So the first thing we're going to do is we're going to talk about the index of a closed path. And this at first seems like a weird notion, but it's not really. All it is it counts the number of times a curve winds around a given point. So the way to think about this is that if you win around it, think about our discussion about how you can have the exact same curve but parameterized differently, right? Like you can go around a curve at different speeds. How would you be able to tell a circle apart that went around 1 time versus one that went on the exact same path around 2 times in the same amount of time, right? How would you be able to tell those guys apart? What's the real difference? Well, there's obviously a difference in the sense that one of them went around once, one of them went around twice. So what the heck? What gives? Well, this is kind of the sort of thing you'd measure by an index. Also, maybe for like weird curvy paths or something like that. And of course, we should do this with respect to the orientation of the path. So if we go clockwise around a point, we'll get an index of -1. So if we go all the way around 1 time clockwise, that's an index of -1. And if we go, say, counterclockwise or usual direction, we can, have crazy self-intersections, whatever the hell else we want. If we go around 1 time, then we'll get an index of 1. If we do it twice, we go all the way around, and then we go around in like a different way. Bada boom, index of 2. If we don't go around a curve, that's an index of 0. Okay. It's not a terribly hard concept. Don't make it any more complicated for yourself than you need to. It's just how many times you go around it, right? And yeah, it's whole business. So the reason that we'll need this is that it's related to something we keep talking about. That is, remember we keep referencing like, integrate around the unit circle, 1 over z dz. And we keep going like, hey, this is 2 pi I, what gives? What's going on? This is going to kind of give us our notion of an index. So here's the basic idea. If gamma is the unit circle, then we know that 2 pi I is the integral about gamma of dz. All right, we just said that out loud. And now the thing to think about is that if you have another closed curve gamma tilde that can be deformed into gamma without passing through 0, that is, if gamma tilde and gamma are homotopic as closed curves in the region A equals C without the origin, that is that punctured complex plane, then again, notice the number of times we'll go around is going to be 1 over 2 pi I times that integral, right? So it's the exact same. So if they're homotopic as closed curves, there we go. And this is generally a reasonable thing to suspect. If gamma tilde and gamma are homotopic in the punctured plane, then it's reasonable that they would wind around 0 the same number of times. I'm going to really highlight that piece, the same number of times. Okay, so maybe for some other point, maybe you're like, what about not 0? What if I want to look at some other point? Well, then we'll just shift this on over. Instead of z, we'll replace it with z minus z naught. That is, we'll translate z naught down to the origin, if that makes sense. Okay, this is, you can get this through the deformation theorem. Fair enough. Okay, so we could just, once again, build out this number of times that we wind around a point by 1 over 2 pi I, integral around whatever gamma tilde dz of z minus z naught. Okay, and so think about it like this. You can pretty immediately get that, all right, do this. Well, you'll get plus or minus 1 if z naught is inside of gamma. Fair enough. 0 if z naught is outside of gamma, right? So for any homotopic, any curve homotopic to the unit circle like this, a simple curve at least, right? Then, and that's important, I guess, for simple closed curves. I should always have been specifying that. But for a simple closed curve, this is pretty clear. You can either wind clockwise or counterclockwise, and you'll go around it once or something like that, right? Just from this formula, say you went around backwards, right? Then you get negative 2 pi I. So divide by 2 pi I, you get minus 1, right? If it didn't have 0 in there, well then by Cauchy's theorem, you'd get 0 out, right? Because it would be analytic on and in the interior of it, right? Okay, fair enough. And so you can just do the exact same thing with a different point, z naught. And so you get plus or minus 1 or 0. Okay. That's for simple closed curve. We can do this in a lot fancier way, and your textbook talks about this a little bit. I've kept the wording right here because it brings up a fun reading topic if you are interested in this. One does have to be careful to define what we mean by on the inside of gamma and outside of gamma. That is maybe not actually as easy of a notion as it immediately appears. What it means to be inside or outside a curve is proving that a closed curve splits something into an inside and an outside is a little bit more of a technically interesting thing to do than you would expect. And that's the contents of the so-called Jordan curve theorem. So if you want to read about that, I recommend, Wikipediaing it and seeing it. It's a fun result. But for all intents and purposes, just think of this in terms of the obvious, okay, a simple closed curve should divide the plane uniquely into two connected pieces, one of which is bounded, that's the inside. And that's essentially all you need to know. So it works the way you think. You've got inside and you've got outside. And here we've got inside, and see, you can kind of get into some more interesting questions of what's inside, right? Inside and outside, blah, 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 right? Okay. So, and I shouldn't have done that for the last one because it's not a simple closed curve, but fair enough right now. So this will give us the notion of an index. So we'll define for gamma a closed curve in C, and z naught a point in C, not on gamma. That's an important bit. This has to actually enclose that thing. It can't pass through the point it's supposed to be winding around or something. Then the index of gamma, as we're going to call it, with respect to the point z naught. This is also called the winding number of gamma with respect to z naught. It counts how many times you wind around. This denoted by I gamma z naught. For some reason, we use a semicolon instead of a comma. This is 1 over 2 pi I times the integral about gamma of dz over z minus z naught. Okay. And we'll say that gamma winds around z naught this index number of times. That is, this index counts how many times you go around the point. And don't get anything more confusing. Don't get confused at all by this. It is exactly as intuitive as you think. In pretty much every situation that we will come across. Don't think that it's always plus or minus 1. This is for this explanation right here, where we're talking about curves gamma tilde and gamma that are homotopic, simple closed curves to the unit circle. For other things, it may not be quite so easy. For, up here, we can pretty easily see that things might wind around more than once, right? But just right now, all you got to think about is that the index is defined like this, and what it does is it counts the number of times a curve gamma winds around a point z naught. Fair enough. Okay. So why do we need this? Well, we'll get to it. It's nice. It's going to let us write analytic functions in a very useful integral form, and this will act as a little nice multiplier that will essentially allow us to account for things like what I talked about earlier with different parameterizations of the same curve, maybe winding around something more times. In the classic Cauchy's theorem case, we don't really have to care about this, because if you're going to get 0 out, then, okay, we wind around more times, whatever. But if we don't get 0 out, then the number of times we wind around maybe does matter, right? That is, if you go around it once and you do the integral, then, you could add it to doing that again, right? And then by the additivity of the contours, you should expect to get twice as much as the curve that goes around it, like twice all at once, right? So think of it like that. We need to keep track of the index to count parameterizations that go speedy around a point or something. That's the easy kind of intuition for why we might care. But let's talk a little bit about the index, and let's get a little bit of an idea about how it behaves. So proposition 2.4.2 has two little pieces. The first piece, the circle gamma of t defined by z naught plus r e to the it. That is a circle of radius r with center z naught, where r is of course greater than 0. And we're of course taking t and 0 to 2 pi n. This curve has index n with respect to z naught. That is, if we take n, we go from 0 to 2 pi n times, right? In terms of the wrapping around, if we go around it n times, then it has index n, because the index counts the number of times we wrap around a point. Of course, if we go in the opposite direction, circle negative gamma, where again, t is between 0 and 2 pi n, if it goes around n times, this will have index negative n. Okay, that's fairly straightforward. If z naught does not lie on either tilde gamma or gamma, and tilde gamma and gamma are homotopic in the punctured plane at z naught, then their indices are the same. The index of gamma and gamma tilde with respect to z naught are the same. So for homotopic curves doesn't have to necessarily be closed curves. Homotopic curves in a punctured space have the same index. So it's a homotopy invariant. That is up to homotopy, kind of continuously deform things. It won't mess anybody up. Okay. So theorem 2.4.3. This is an important thing to establish, though it seems kind of obvious, especially if we are just defining, the index to be the number of times we wrap around a point, or wrap around a point with a curve, right? But given our definition, it is important to actually verify that we are counting the thing we want. That is, theorem 2.4.3 says Given gamma, a function from the closed interval a, b into c, and I just noticed that we are missing a colon right there. Okay, there we go. So gamma, a function, piecewise C1, I guess, of course, closed curve from the interval a, b to c, and a point z naught not on gamma. All right, what we want to say is that this index is an integer. That is, if we're saying that the index counts the number of times a curve wraps around a point, that is how many times gamma goes around z naught, then we should be careful to make sure that however we've defined it, we actually get out a whole number, right? I mean, you could maybe say like, well, what if you went halfway around it? But that gets a little bit harder to talk about. And so let's just leave it in terms of, how many full times do you wrap around it? You either wrap around it a full time, since it's a closed curve, right? It can't be a closed curve and you can get halfway around it, right? I mean, maybe if you want to be very fancy, you could somehow come up with some sense where you could say that. But in terms of how we've said things, this doesn't make any sense right now. You can either go around something, since you have to end where you start, or, you can not go around it. There's 0 or some number of times that is a whole number. How do we know that it's an integer? Let's go. Okay, so for our proof, we'll let g of t be equal to the integral from a to t of gamma prime of s over gamma of s minus z naught ds. So remember, gamma is from ab to c, so this is from the starting value until something right there. So g of t will of course be defined on ab once again, right? Okay, so at points where the integrand is continuous, that is at points where this business there, right? The fundamental theorem of calculus will of course tell us that take the derivative and we'll get, well, the inside business, right? So g prime of t is equal to gamma prime over gamma minus z naught. All right, the right-hand side is the so-called logarithmic derivative. If you took Calculus 1 with me, I talked about logarithmic derivatives a lot. It is a important thing it is a great tool, logarithmic derivatives. It's the logarithmic derivative of gamma of t minus z naught. Kind of using the exact same sort of thing we would expect to get out of a logarithmic derivative, something of that effect. Just think about using the product rule. What we're seeing up here is saying that the derivative with respect to t of e to the negative gt times gamma of t minus z naught is 0. Why would this be? So logarithmic derivative, what do you think is gonna, why do we call this logarithmic derivative, by the way, just in case you're not seeing it? Let me put this as like a little sidebar. So just think of like classic Calc 1, right? You get what? Derivative of the inside, f prime of t, times the derivative of the outside evaluated at the inside. What's the derivative of natural log? It's 1 over, natural log of t, 1 over t. And so you put, right? And so, hey, take gamma t minus z naught. Oh, look, that's exactly what you get down there, and the derivative of that is on top. So it's exactly the same kind of thing you see right here. Logarithmic derivative of the logarithm of something. So if you took e to the negative that, right, and you took a derivative, you would expect to get what? Well, I mean, just actually go through and calculate this out, and you'll get exactly this. I won't take too much time belaboring the point. You get this at points where g prime of t exists. Thus, e to the negative g of t times this quantity is piecewise constant on AB, right? That is, it has a 0 derivative, so it's got to be constant. It could maybe jump around at places where g prime of t doesn't exist. That is, at places where gamma of t equals z naught, something like that. Oh, okay. But wait, this guy is continuous, so it has to be constant. That is, notice this this bad boy, the place that could stop this from happening, right? That would be, well, you don't even need to go that far. Here's all you need to point out is that this is continuous. And so if it's continuous, then we can't be jumping around like this, right? Okay, can't be jumping around to like different little constant chunks. So then it just has to be constant on, it must be constant on this entire interval. This constant value is, well, just throw in a value. If it's the same everywhere, then you can definitely throw in A and get it out, right? Because it doesn't change. Okay, so just throw in A for T, and hey, what are you going to get? Well, you get the same thing as when you throw in B. It's the same thing when you throw in B right there, right? Okay, cool. But gamma of B is equal to gamma of A. So e to the negative g of B is equal to e to the negative g of A. On the other hand, g of A is 0. Hence, e to the negative g of B is 1. Thus, g of B is 2 pi ni for some integer n. Huh. How about that? G of B is 2 pi ni. But what is g? Well, wait a second. G of B is exactly equal to the index. That is, just put a b right in here. Hey, look. This is the index of our curve gamma about, or with respect to, z naught. That is, notice this is just the integral about gamma of 1 over z minus z naught dz, right? Just, plug in gamma, do chain rule, right? Bada boom. Okay. Ooh. That's pretty cool. So if g of b is equal to, it's not quite actually, I should be clear, this is 2 pi I times the index, right? Because you have to have divide by 2 pi I, or, right? This is g of b. I should put a 2 pi I there as well. And I should put a 2 pi I here as well. Or actually, I shouldn't put a 2 pi I there. I'm sorry. I'm being too hasty. It's Monday. It's a Monday. I was right there. This is 2 pi I times the index. Because the index has this bad boy divided by 1 over 2 pi, or multiplied by 1 over 2 pi I. So that's why we get the 2 pi ni right here. So divide by 2 pi I on both of them, and you get that the index is an integer, right? Because the complex exponential is 1 precisely when these things are equal to integer multiples of 2 pi I, right? Okay, there we go. Easy enough. All right, so I'm sorry if I butchered that at all. And now we're on to the big exciting part. I wanted to get through that because here's the big deal. This is the main attraction. This is what's exciting here. We're going to figure something out that's kind of amazing, and that is nowhere near as impressive as it actually is on the first glance. So let's state the theorem, and then let's talk about why it is so cool. Okay. This theorem, Cauchy's integral formula, says that if you have an analytic function on a region A closed curve gamma in a region A that is homotopic to a point, and a point z naught in A that is not on gamma, then the value of f at z naught times the index of gamma with respect to z naught is equal to 1 over 2 pi I times the integral of f of z over z minus z naught about gamma, the contour integral about gamma. This is kind of crazy. Just sort of rewrite this bad boy really quick. This tells you that f of z is equal to, write it like this, 2 pi I index gamma z naught. And this is, of course, assuming that the index is non-zero, right? This is why we write this over here, because if the index is 0, then we wouldn't want to divide by it. So assuming the index is non-zero, then I'm going to use a different variable than z. I'll use a zeta d zeta. So notice this just says that you can figure out the value of a analytic function at a point by looking at some sort of an average of how it behaves on a curve gamma surrounding that point. Huh. Provided that it's analytic and all these, like, nice conditions right up here. But provided that those conditions are satisfied and gamma is like a good curve with respect to, I should not use z naught right here. Sorry, I was rewriting too fast. Just z in this case, because I'm trying to say that. Let me make that a little cleaner. What I'm trying to point out here, and that's not absolute values, that's just a parenthesis, just to try to make it cleaner, and it made it worse. What I'm trying to say right here is that this is crazy because it tells you that the value of a analytic function at a point is determined by the values, an average of the values of that function near that point, which is weird. It means that the behavior of f here is determined by the behavior of f here and here and here and here on any of these curves. That's nuts. That is absolutely nuts. That is such a ridiculously strong condition. And this sort of tells you something about the rigidity of analytic functions, how restrictive this class is, how few of them there are. And it is similarly to, like, being a conformal mapping or something. It is like it is not clear at all how you would just construct these kinds of things just without, if someone said, like, hey, give me a function that does this, you'd be like, God, I bet those functions have to be so crazy. But it's amazing that it's just the complex notion of differentiability gives you this. What a absolutely nutso result. And this will make you mad about all of the calculations that you have done in previous homework assignments, because you will go, God dang it, I could have done that so quick. So for example, this formula is applied all of the time when gamma is a simple closed curve and z naught's inside of gamma so that the index is 1. Then the formula is just what I wrote, that you can just evaluate. And you can also do it if the index is like 2, but why not just do it with one that's equal to 1, right? And then you can just get, okay, it's 1 over 2 pi I times this nice integral, right? So for example, if you wanted to say, oh, I don't know, figure out what the value of sine of e to the z is at, say, like 0. Well, you'd be like, oh yeah, I can go calculate it all out, okay, blah blah blah. But you could also, do some easier stuff. And similarly, you could just use this formula. Similarly, you can calculate contour integrals, this right-hand side, in terms of the value of the function at one point. So if you have a difficult contour integral, you can just evaluate a function at one point, multiply it by 2 pi I, and you're done. That's amazing. You don't even have to do integration, basically, if you don't want to. You can just do function evaluation. It's amazing. So much easier than in the real case. It says that in a fundamental way, the value of f is determined by its boundary values. That is, the values of f on gamma determine the values of f inside of gamma. It's like I said, like, the point behavior right here depends on the behavior out here, and it depends on the behavior out there, on, like, all sorts of crazy curves. It's an amazing condition. So what do we get out of Cauchy's magic formula? Well, this bad boy right here has a good proof that we will talk about. But we get quite a lot of things out of this. And one of the things we're going to get out of it that I think you should watch for as we're going through this proof, because you'll see hints of it if you're paying good attention, is that this will let us get interesting information about how many times a analytic function is differentiable. That is, we know that we can talk about through some of the things we've done before whether or not things have antiderivatives, nice analytic antiderivatives and so on, right? But what about the analyticity of the derivative? That is, do analytic functions have analytic derivatives? It's a good question. This will maybe let us find something out about that. It is definitely not the case for real valued functions. Notice real valued functions can be, say, continuously differentiable without having a derivative that is also continuously differentiable. You can have that break down pretty quickly. Is the same true for analytic functions, or do we diverge? Okay, we're going to get stuff out like that. So let's talk through this proof, and then let's start exploring some of its consequences. So the Cauchy integral formula: f is analytic on a region A. Gamma is a closed curve in A that is homotopic to a point. This is a big deal. And z naught is in A. It's a point that's not on gamma. So it doesn't have to be inside of gamma, though it can be. Okay. Then we get this nice formula that I have opined on at length. And this is what we're going to show that it's true. Okay. So how are we going to do this? Let's start out by letting g of z be equal to f of z minus f of z naught over z minus z naught, whenever z is not equal to z naught, because otherwise this bottom would have a 0 right there. Then we'll let it be equal to f prime of z naught if z is equal to z naught. Okay, so notice since the definition of the derivative f prime of z naught is going to be equal to the limit as z goes to z naught of f of z minus f of z naught over z minus z naught. So this will obviously be continuous, right? Since, it approaches that value. It's definitely analytic since the top is analytic and the bottom, everything's good, f over g, right? Everything's good, it's all analytic, except perhaps at z naught. And continuity, by what I just pointed out there, is obvious. Okay. Now, so we have analytic, except potentially at this one spot, continuous at that spot. Okay, so we integrate it around a closed curve. We get 0. Okay, so 0 is this integral. All right, then plug in what the heck we've got. Well, f of z over z minus z naught minus f of z naught over z minus z naught. Fair enough. But what is this right here? F of z naught right here? Oh, hey, look. Pull that f of z naught out. I've got this integral about gamma of 1 over z minus z naught dz. That's 2 pi I times the index of gamma about z naught, and with this f of z naught factor. Hey, this is 0. So this thing equals that thing, right? Scratch that out so then I have this statement. See what I'm saying? This thing equals that thing. This thing right here is 2 pi I f of z naught index gamma with respect to z naught. So just divide by 2 pi I and you're done. That's pretty easy. That just is a direct result of Cauchy's theorem. Not a terrible proof in the slightest. Not even remotely as difficult as some of the things we've been doing with like Gorsat's method of repeated bisection and all that sort of stuff. Wonderful. And this is just the most useful result. I have been waiting for us to finally prove this because it is so painful to calculate contour integrals by hand when you know about this result. Now that you know about it, you will never have to do it again, hopefully, except to check your work because it's a good thing to do and, you should do it occasionally. But hopefully you don't really have to do it very much because it's so nice to use this theorem. For example, this is just fantastic because, hey, for example, if you've got gamma, the unit circle, then, oh, hey, look, integral about gamma of e to the z over z d to z. This looks like, oh, if I had to do this by hand, this would be annoying. We wouldn't like it very much. But we could do it, but we'd just be sad about it. Okay, we could go through and we could do it. But, hey, wait a second. E to z, that's entire, so it's analytic everywhere. And so gamma, the unit circle, this is certainly a closed curve in the region of analyticity of the exponential function, and it definitely contains, point 0, right? Okay, cool. So, the behavior of it at 0 is, there you go. And then you just plug it on in, e to the 0, 2 pi I, index is 1, right? Bada boom, 2 pi, easy. What? How simple is that? Isn't that wonderful? It's the easiest thing in the world. Okay. So what you're seeing here, these kinds of integrals, like where you get like I've written before, like evaluating functions using the Cauchy's formula is a pretty cool trick, and we call these integrals of Cauchy type because of the obvious reason. And this is something like a function like g of z 1 over 2 pi I integral about gamma g of zeta, zeta minus c, d zeta, like I was writing out before. So something I'd be interested in is, hey, what kinds of functions can I represent this way? It's a good question. I know that when I have an analytic function and an appropriate curve and an appropriate z naught, I know I can do this business right here, right? Notice how did I know to use 0, by the way, in this? I should have made that more clear in case that wasn't obvious, because we got the whole z minus z naught. What is the z naught down here? It's 0, right? Z minus 0 is z. So I know that I should use 0. So that's 2 pi I times the index, which we know is 1, and then plug in 0 to the top function. And that's how we got that out. But yeah, anyways. So we've got this f of z, z minus z naught dz. All right, we know that we can represent analytic functions at any point in terms of this. So for like an entire function, right? Entire functions have representations anywhere in this way, right? With respect to a given curve, right? Okay, cool enough, easy enough. So what other functions can I represent this way? That is, if I build a function g in this way, what properties can we discover about it? What is the differentiability of a Cauchy type integral? And that's the question we answer in theorem 2.4.5. If gamma is a curve in the complex plane and g is a continuous function defined along the image of gamma that is along that curve, then if we take a Cauchy type integral using g like this, let's call that big G. Then big G, what we're going to claim, big G is analytic on the entire complex plane except potentially on that curve. In fact, G turns out to be infinitely differentiable with its kth derivative given by, and this is amazing, almost the exact same formula, except instead of a 1 now I have a k factorial up top, and instead of a zeta minus c down below, I have a zeta minus c to the k plus 1. That's the only difference. So we just take powers in the bottom. Nothing else happens. It's the simplest thing in the world. It is amazing. All right. So we can calculate all of its derivatives in an obvious and nice way. Cool. You can think about this, the formula for the derivative. You can remember it by differentiating with respect to z under the integral sign, as it's called. This was a favorite trick of Feynman, for example. So the trick here is take the derivative with respect to z of g of z, right? This integral of Cauchy type, 1 over 2 pi I, of course. Pop that out. d dz of this integral, right? And then we're just basically going to pull in a partial with respect to z like that, right? And when we do that, we just differentiate on the bottom. Hey, nice. So it's just the obvious thing to do. Yeah. Easy. Okay. Simple. Fair enough. So there is a proof for this that we can talk about. I'm skipping it for the moment, because I want to move on to this next part, and because we won't have time for it in class today. If we have time for it tomorrow, we'll do it. It's a little bit longer than what we've done so far, but it is a useful thing to talk about. So, because it does answer the useful converse, which is not, I would say, immediately apparent. We know that we can represent analytic functions with respect to nice curves at certain points in this way, but are all of the functions that we can represent in this way analytic? Is the answer to that is not immediately obvious, and so proving that that's true is a good thing to do, and we will if we get time, but it is not the most enlightening proof. It is in your textbook, and we won't spend too much time on it quite yet. What we'll instead say is Cauchy's integral formula for derivatives, which is a sweet result, just basically applying the exact same thing as before to the case where we are already dealing with an analytic function. So if we have f an analytic function on a region A, this is amazing. All the derivatives of f exist on A. That is, being analytic means you're infinitely differentiable. So this nice complex differentiability is the same as infinite differentiability. It's amazing, and it should be like that is shocking to me, and it should be shocking to you too, because you know that there are functions that are differentiable once in the real numbers that are not differentiable twice, let alone continuously differentiable. It is a much messier situation when you're dealing with the reals, but as is almost always the case, once you start dealing with the complex plane, things get nice. So this is nuts. We have infinite differentiability here. Okay. And furthermore, for a point z naught in this region of analyticity, and gamma any closed curve homotopic to a point in A with z naught not on the curve itself, then we can represent not only the values of f, but the values of its derivatives in terms of similar Cauchy type integrals. That is, the kth derivative of f at z naught times the index of gamma with respect to z naught is k factorial over 2 pi I, this little multiplying factor, times the contour integral about gamma of f of zeta over zeta minus z naught to the k plus 1 d zeta. Or we could do z's there instead of zetas if you wanted. And that's wild. Where, of course, f with this little parenthesis k means the kth derivative, in case you haven't seen that. But that's nuts. That blows my mind. I mean, it's kind of obvious, I guess, once you prove that all the derivatives of f exist in A, because, well, as soon as you know that you got a derivative, then you can use the Cauchy integral formula again on the derivative. But the amazing thing is that it also still looks this dang nice, and you're just getting these k plus 1s down below. Oh, amazing. It's a beautiful thing. It's a beautiful thing. So whether we'll have enough time to go through this proof, I don't know. It is a little bit, we'll have a few minutes. It won't take more than a few minutes. We'll do it tonight. So let's go through this proof, and then we'll call it quits. So since A is open, it's a region, right? Since A is open and Z naught is not in gamma, we can always find a little circle, let's call it gamma naught, centered at Z naught, whose interior is in A, and such that gamma does not cut across gamma naught. That is, if you've got a point and you've got some kind of a curve around it, even if the curve is sort of nutso or something like that, you could always find like a little tiny circle that goes around that and stays in that curve. Not too crazy. Looks like this picture, right? You've got gamma here. I was trying not to have to go around this, but here we even have one that's not pretty curve. This has self-intersections and all sorts of stuff. We got some closed curve here, and we can always grab some little tiny circle gamma naught about Z naught. All right, and all of this stays inside of A. Nothing's too crazy here. Okay. Now, for Z and A, not on gamma, of course, let's define an integral of Cauchy type. That is, this will be f of z times the index of gamma with respect to z. And just by the definitions of those things, this is this integral of Cauchy type, 1 over 2 pi I, the integral about gamma, the contour integral, f of zeta, zeta minus z d zeta. All right, just from the definition of this bad boy right here. Okay, cool. So, integral of Cauchy type, it's infinitely differentiable on A sans gamma by our this unproven theorem 4.25 over here. Okay, infinitely differentiable there. So obviously this is relying very heavily on this theorem we didn't actually prove quite yet. And we're also getting, of course, this formula from the theorem we didn't quite prove yet. But here's just a little thing to kind of connect the dots and hopefully bring it home, so that as long as you accept that theorem we haven't proven yet, you can see where it all comes from. But f of z is, of course, equal to 1 over 2 pi I times the integral about gamma naught of f of zeta over zeta minus z d zeta, right? Because it's analytic. Okay. And this is, we're just going to, and oh, here, okay. So this integral right, or this, sorry, not to throw anything off, this index right here, right? 1 over 2 pi I, integral about gamma, 1 over zeta minus z d zeta. These guys are also integrals of Cauchy type. So they are also infinitely differentiable near z naught by this as of yet unproven theorem, right? So, okay, since the index is constant, except where z crosses the curve, in particular, it's constant, of course, inside of gamma naught, then notice that since we could replace then this z with a z naught, since it's constant, and we're not going to get anything different, right? And we throw this in here. Okay, all good. Combining this with the preceding formula for the kth derivative, this guy right here, we get our desired result. How do we get it? Well, all we're trying to say, if you're seeing it, you got f of k, z naught, index, want to get out this nice integral of Cauchy type. We've got the right-hand side of it right there, right? Everything's all good. We need f of k z naught, index gamma z naught. Now, g right here, yeah, this business. So the kth derivative is ever, sorry, I feel like I'm being too pedantic here. This is that piece. Sorry, I think I'm hammering this point too hard. This is pretty straightforward. You see it. I don't need to write it all out. We'll touch on this again with the longer proof of it next time, and hopefully that'll make it more enlightening if this doesn't seem enlightening yet, since this is basically a proof by like, just look at the other theorem, which is maybe not super enlightening, considering that we didn't actually prove that one yet, but we'll prove that one next time. I think we'll have time for it, because all we have left to talk about after this is a fun little inequality, Cauchy's inequality. This gives us something called Liouville's theorem. We'll, as a nice little exercise, prove the fundamental theorem of algebra using this. And then we'll talk about a very important result called Morera's theorem, which gives us some kind of a converse to Cauchy's theorem. So we'll do that, and we'll prove this result right here, this theorem 2.4.5. And then we can talk about this one a little bit more in case people don't like the proof without understanding why this holds. So we'll get to that next time. The cool thing here that you should take away from today is that Cauchy's theorem lets us understand that analytic functions have analytic derivatives, which is nuts. And their behavior at a point is determined by their behavior near a point. Um, in in a way more um, powerful than continuity. Like obviously, if you have a continuous function, then what it's doing nearby sort of tells you what it has to do at a point. But this is further away. This is on any curve that encircles a point, provided it's a nice curve with respect to the analyticity of the function. So that's kind of nuts. We'll get into this a little bit more next time, and I'll stop rambling for today. So um, cool. If you got any questions or want to know anything before the exam, shoot me emails, and I'll see you next time.